I mentioned earlier that the wind load should be analyzed with all the loads acting simultaneously, not wind by itself. In the same sense that we looked at the thermal effects by subtracting the operating minus the installed. Or if we're talking about seismic loads and you wish to include nonlinears, it'd be wise to look at operating plus seismic minus operating to extract the pure seismic component. This presentation will go through that in a little more detail. So we're now talking about occasional stresses. Now, CAESR 2 does not recommend occasional load sets. What we would suggest you do when you build your own, don't look at the occasional by itself, but do the same thing we did with our thermal case. Say operating state with the occasional load minus the operating state will give you the response due to the occasional load. So let's take a look at that. Here we have a model. Let's say it's a linear model, and I have weight, temperature, and pressure, and also wind 1. Now, CAESR 2 will recommend the operating case, the installed, and the difference, and you as a user will have to incorporate your wind loads. Now, if the model's linear, you could introduce load case number 3 to get the wind loads, the wind stresses, and then add the sustained stresses to these occasional stresses to evaluate the magnitude of the stresses. So load case 3 will calculate the occasional stress, and load case 5 will evaluate the sustained plus occasional stress. But if we have a nonlinear system, we can't isolate the wind loads by themselves here. We would recommend that you run an operating with wind, just throw them all together, and the operating state, when you subtract that from the wind case, will give you the wind response. Operating plus wind minus operating equals wind. And since it's nonlinear, we're going to have to do plus wind and minus wind. Here's an example. I'm looking at a riser. Let's say I'm up a long riser line here, horizontal direction. I've got a gap on a guide, equal gap on either side. And I'm going to do a wind load in the x direction. So if I run wind 1 by itself, the wind magnitude is not large enough to close the gap. So the support is not taking the load, but the pipe is taking the load. I could say, well, maybe that's my wind load, then I have to add those to my sustained case, and that's my wind evaluation, positive wind evaluation. And if I blow the wind in the other direction, I'm just using minus wind 1, rather than defining a different vector. I will then have to add those stresses to sustained stresses. So load case 7 is sustained plus occasional for the negative x wind load. But that's really not the true starting point of this load. We really don't have an equal gap on either side. We're actually starting from the operating position. So I'm saying the piping system moves here in the operating position. And now the effective gap I have in the x direction is very small, and the effective gap I have on the negative x direction is much larger. And we see that there's a price to pay for this more exact analysis. So we're showing load case 3 is operating plus wind, and in load case 3 the guide is engaged. So now the wind is going into the structure and not loading up the pipe as much, and not so much bending the pipe. So how much wind load was actually put in the positive x direction? Well, that's found in load case 5, 3 minus 1. Operating plus wind minus operating, and that's the vector we get. Compare that to the magnitude of the vector with wind 1 by itself. Different magnitude. And if I blow the wind in the other direction, now with this larger gap, I get the same response in the negative x direction as I got wind alone. But this process here will work in every case here. So as you can see here, I will have a rather simple set of load cases get a little more complicated, but if you understand how CAESR 2 is working, then this should make sense. Operating minus wind, subtract those two, L4 minus L1 will give me my occasional stresses alone. But again, B31.3 and other codes say you can't evaluate these collapse loads alone. Instead, you have to sum them with the other collapse loads, your sustained loads, and they must be less than a value greater than SH. This is the recommended procedure that we would give you if you are doing nonlinears with occasional loads. So in closing, if I have a plus y support in my model and I intend for it to carry dead weight and there is liftoff, is that really a good location for a dead weight support? So we're getting into these questions. We can solve a lot of problems that have nonlinear conditions in them, but in terms of good design, I don't think we're answering the question. If I want the support to carry dead weight, I should have it carrying dead weight in both the installed and operating position. Another way of saying that is simply because you can model it in Caesar 2 does not mean it is a good design. We have a lot of capability in nonlinears in Caesar 2, but use them wisely. Like I said before, you might want to run both with friction and without in the same analysis to evaluate the effect of friction in that specific model. And don't put tight little gaps on guides if you do not control those gaps out in the field. Don't play games with the software. Make it reflect what's actually going on in the field.